Picture this: the universe keeps a ledger of everything it contains, a cosmic inventory of all the matter that makes up galaxies, stars, and even you. But there's a problem. When scientists checked the books, half of the normal matter in the universe was missing. Not dark matter, not some mysterious unknown substance, just ordinary matter, the stuff we're made of. Gone, vanished, and nobody knows where. This isn't science fiction. It's one of the biggest unsolved puzzles in modern astrophysics. Where did half the universe's baryons, the particles that form atoms, planets, and everything we see, disappear to? Somewhere between the fiery aftermath of the Big Bang and today, these building blocks of reality slipped through the cracks. They didn't just evaporate. They're hiding, invisible, not because they're dark, but because they're scattered in places so faint and diffuse that even our most powerful telescopes struggle to find them. The answer might lie in an unimaginably vast web of superheated gas stretching between galaxies, a ghostly structure we've only just begun to map. So, where is half the universe's normal matter? The hunt is on, and the answer could rewrite our understanding of reality. Stay with me as we unravel this cosmic detective story piece by piece. Now, let's dig deeper into the heart of the mystery, the baryons themselves. Imagine baryons as the universe's most fundamental construction crew. They're the particles that build everything you can see, touch, and even breathe. Protons and neutrons, the tiny heavyweights inside every atom's nucleus, are baryons. Without them, there'd be no stars lighting up the cosmos, no planets orbiting them, and no you or me wondering about all of it. Here's why they matter so much in this cosmic accounting problem. Baryons make up what scientists call normal matter, the stuff that interacts with light, gravity, and the other forces we understand well. When you look up at the night sky, every twinkling star, every swirling galaxy, even the faint glow of distant gas clouds, they're all baryonic. But here's the twist: baryons are only about 5% of the universe's total mass and energy. The rest, that's where dark matter and dark energy come in. Two enigmatic players we'll touch on later. Dark matter, for instance, doesn't play by the same rules. It doesn't emit, absorb, or reflect light, making it invisible to our telescopes. Yet, its gravitational pull is so strong that it shapes entire galaxies. Baryons, on the other hand, are the visible glue holding the universe's structure together. They form the raw material for stars, which forge heavier elements in their cores, scattering them across space when they explode. Those elements, carbon, oxygen, iron, later become planets, oceans, and life. But here's where things get puzzling. If baryons are the universe's known building blocks, why can't we find half of them? We've counted the ones locked in stars, planets, and interstellar dust, but the numbers don't add up. It's like knowing you have 100 puzzle pieces, but only finding 50 on the table. The rest must be hiding in plain sight, just in forms we've overlooked. So, what's the takeaway? Baryons are the universe's tangible, measurable matter, the part we thought we understood. Their disappearance isn't a magic trick. It's a clue that our cosmic ledger might need a second look. And as we'll see next, the hunt for these missing pieces takes us into some of the most extreme and elusive corners of space. Let's zoom out for a moment and talk about the cosmic ledger, the universe's grand accounting system. Scientists have spent decades tallying up all the matter we can observe, from the brightest galaxies to the faintest wisps of gas. They use some ingenious methods to do this. For example, by studying how light bends around massive objects, a phenomenon called gravitational lensing, they can weigh entire galaxy clusters. Another approach involves analyzing the cosmic microwave background, the faint afterglow of the Big Bang, which gives us a snapshot of how much ordinary matter existed in the universe's infancy. Here's where the numbers start to tell a strange story. When researchers add up all the baryons they can see, stars, planets, nebulae, and the gas within galaxies, they only account for roughly half the amount predicted by our best theoretical models. Those models, grounded in the physics of the early universe, suggest there should be far more normal matter out there. It's not a small oversight, it's a gaping hole in our cosmic budget. This is the essence of the missing baryon problem. Think of it like balancing a checkbook where half your money has vanished without a trace. You know it should be there because the math says so, but no matter how carefully you search, you can't find it in the usual places. Scientists face a similar frustration. The missing baryons aren't just hiding behind the cosmic couch, they're eluding detection across vast stretches of space. One clue comes from the early universe. Moments after the Big Bang, conditions were so extreme that protons and neutrons formed in precise ratios, leaving behind a chemical fingerprint we can still measure today. This process, called Big Bang nucleosynthesis, tells us exactly how much baryonic matter the universe started with. Fast forward billions of years, and that number hasn't changed. Matter can't just disappear. So if we're only seeing half of it now, the rest must be lurking somewhere unconventional. The hunt for these missing baryons isn't just academic. Solving this puzzle could reshape our understanding of how galaxies form, how cosmic structures evolve, and even how the universe distributes its building blocks over time. It's like realizing there's an entire hidden chapter in the story of everything, one we've only just begun to read. Now, as we turn the page, we'll explore where scientists think these elusive baryons might be hiding and the clever tools they're using to track them down. The answers, as you'll see, take us into some of the most extreme and least explored realms of the cosmos. To piece together this cosmic puzzle, let's rewind the clock way back to the universe's first few minutes. In the fiery aftermath of the Big Bang, the stage was set for a remarkable process that would leave an indelible mark on the cosmos: primordial nucleosynthesis. During this brief but critical window, temperatures and densities were so extreme that protons and neutrons could fuse, forming the first atomic nuclei. This wasn't just random chaos, it was a precise, predictable reaction governed by the laws of physics. The outcome, a cosmic recipe that tells us exactly how much ordinary matter the universe began with. Here's why this matters. The ratios of light elements created during nucleosynthesis, like hydrogen, helium, and trace amounts of lithium, serve as a time capsule. By measuring these abundances today, scientists can reverse engineer the conditions of the early universe. The results are astonishingly consistent. Baryonic matter made up about 5% of the universe's total energy budget at that time. Fast forward 13.8 billion years, and that number should still hold true. Matter doesn't just vanish, it transforms, moves, or hides, but the cosmic microwave background adds another layer of confirmation. This faint glow, often called the universe's baby picture, reveals tiny fluctuations in temperature and density from when the cosmos was just 380,000 years old. These fluctuations are like fingerprints, encoding information about how matter was distributed back then. When scientists analyze this data, they arrive at the same conclusion: baryons should account for roughly 5% of the universe's content. Yet today, when we tally up all the visible matter stars, galaxies, and the gas we can detect, we're coming up short by half. So where's the disconnect? The early universe's ledger is pristine, but somewhere along the way, half the entries got smudged. Perhaps the missing baryons aren't in the obvious places, but woven into the fabric of space itself, in forms too diffuse or energetic for our current tools to spot. Or maybe they're tucked away in regions so vast and faint they've escaped notice. What's fascinating is that this isn't just about finding missing matter, it's about understanding the universe's scaffolding. Baryons are the raw material for everything we see: planets, stars, even life itself. If half of them are MIA, it means we're only seeing part of the story. The next chapter takes us deeper into the cosmos, where the hunt for these elusive particles leads to some of the most enigmatic corners of space. Now, let's zoom in from the grand tapestry of the early universe to the galaxies we see today. These glittering islands of stars, gas, and dust are where we'd expect to find a significant chunk of the universe's baryons. After all, galaxies are the most visible reservoirs of ordinary matter, dazzling us with their luminous splendor. But when scientists meticulously tally up the baryons here, the numbers tell a puzzling story, one that doesn't quite add up. Modern telescopes, from the Hubble Space Telescope to ground-based observatories like the Very Large Telescope, have given us an unprecedented view of galactic structure. They reveal stars clustered in swirling arms, vast clouds of molecular gas, and dusty lanes weaving through the cosmic landscape. By measuring the light emitted by these components, astronomers can estimate the total mass of baryons locked within galaxies. Stars, for instance, are relatively straightforward. Their brightness and color betray their mass. The gas and dust, though trickier, can be mapped using radio waves and infrared light, which pierce through obscuring material. Yet, even when we account for everything visible, stars shining brightly, gas glowing in nebulae, and dust dimming starlight, the total barely scratches the surface of what primordial nucleosynthesis and the cosmic microwave background suggest should be there. In fact, galaxies collectively account for less than 10% of the expected baryonic matter. That's a staggering shortfall. Where, then, is the rest? One clue lies in the outskirts of galaxies. Observations of galactic rotation, curves, how stars and gas orbit a galaxy's center, reveal that visible matter alone can't explain the gravitational forces at play. This discrepancy famously led to the proposal of dark matter, but it also hints at something else: vast, faint halos of hot gas surrounding galaxies. These halos, detected in X-rays by observatories like Chandra, are so diffuse they're nearly invisible, yet they contain a significant fraction of a galaxy's baryonic mass. Still, even when we add these halos to the ledger, the numbers remain stubbornly incomplete. Another piece of the puzzle comes from galactic winds. Supernova and active black holes at the hearts of galaxies can blast material outward at incredible speeds, ejecting baryons into the intergalactic void. These outflows, rich in heavy elements, have been spotted by ultraviolet and X-ray telescopes. But while they explain some of the missing matter, they don't account for the full deficit. What's becoming clear is that galaxies, for all their brilliance, are just one chapter in the story of baryons. Much of the universe's ordinary matter isn't neatly packaged in these stellar metropolises, but scattered far beyond, in regions so vast and tenuous they defy easy detection. The hunt now turns to the spaces between galaxies, where the true hiding places of these elusive baryons may lie. Now, let's venture beyond the familiar glow of galaxies into the vast, seemingly empty stretches between them. This is where the intergalactic medium, or WHIM, comes into play, a diffuse sea of gas so thin it's nearly invisible, yet it might hold the key to solving the missing baryon mystery. Think of it like the ocean's surface on a windless day, calm, almost undetectable, but hiding immense depth beneath. The IGM is far from empty. It's a web of incredibly low-density gas, primarily hydrogen and helium, stretched across the universe in a sprawling cosmic network. Unlike the dense pockets of matter in galaxies, the particles here are so spread out that a cubic meter of IGM might contain just a single atom. Compare that to Earth's atmosphere, which packs trillions of molecules into the same space. This extreme sparseness makes the IGM extraordinarily difficult to detect. You can't just point a telescope at it and see a glowing structure. Instead, astronomers have to rely on indirect methods, like catching whispers of its presence in the light of distant objects. One way scientists probe the IGM is by observing quasars, the brilliant cores of active galaxies billions of light years away. As their light travels through the cosmos, it passes through filaments of the IGM where atoms absorb specific wavelengths. This leaves behind absorption lines in the quasar's spectrum, like fingerprints revealing the composition and density of the gas. The most famous of these are the Lyman alpha forests, dense thickets of lines caused by hydrogen atoms absorbing ultraviolet light. By decoding these patterns, researchers can map the IGM's structure and estimate how much matter it holds. But here's the catch: not all of the IGM's baryons are cold and neutral. A significant portion is thought to exist in a hotter, ionized state, where electrons have been stripped from their atoms. This phase, known as the Warm-Hot Intergalactic Medium, or WHIM, is even trickier to spot because its emissions are faint and scattered across X-ray and ultraviolet wavelengths. Detecting it requires instruments like NASA Chandra X-ray Observatory or the European Space Agency's XMM Newton, which can pick up the faint glow of million-degree gas. Even then, the signals are often buried in noise, like trying to hear a whisper in a crowded room. Despite these challenges, the IGM, especially the WHIM, remains one of the most promising hiding places for the universe's missing baryons. Simulations of cosmic structure formation show that as the universe evolved, gravity pulled matter into filaments and nodes, creating a vast cosmic web. The WHIM is thought to reside along these filaments, a faint but pervasive scaffolding connecting galaxies. If confirmed, this would mean that what we once considered empty space is actually a dynamic, bustling highway of matter, just in a form we're still learning to see. So why hasn't the IGM given up all its secrets? Part of the problem is technological. The signals from the WHIM are incredibly weak, and current telescopes often lack the sensitivity or resolution to distinguish them from background noise. Another issue is the sheer scale of the IGM. Its filaments span hundreds of millions of light-years, requiring vast observational campaigns to map even small sections. And even when we do detect it, calculating the total mass of baryons present involves complex models and assumptions, leaving room for uncertainty. Yet, every flicker of detection brings us closer to solving the puzzle. Recent studies, like those using the Hubble Space Telescope's Cosmic Origins spectrograph, have claimed to spot signatures of the WHIM in the absorption lines of oxygen ions, a tantalizing hint that we're on the right track. The next generation of telescopes, like the upcoming Athena mission, promises to sharpen our view, potentially turning these whispers into a clear chorus. The IGM challenges our perception of the cosmos, reminding us that the universe's most important structures aren't always the brightest or most obvious. They're the subtle threads weaving everything together, quietly holding half of reality's ordinary matter just out of sight. Now, let's take a closer look at the Warm-Hot Intergalactic Medium, or WHIM, the most elusive suspect in the case of the missing baryons. Imagine a cosmic crime scene where half the evidence has vaporized into a ghostly haze, scattered across the universe in a form so faint it's nearly invisible. That's the WHIM, a theorized network of ionized gas, superheated to temperatures between 100,000 and 10 million degrees, threading the spaces between galaxies. Unlike the cooler, neutral hydrogen we see in the Lyman alpha forest, the WHIM is a seething ocean of charged particles. Protons, electrons, and heavy ions like oxygen and neon, all stripped of their electrons by extreme heat. This ionization makes it incredibly difficult to detect. Neutral gas absorbs light in specific, recognizable wavelengths, but the WHIM emissions are faint and spread thinly across X-ray and ultraviolet spectra. Spotting it is like trying to find a single lit match in a foggy field at night. So how do astronomers even begin to hunt for something this elusive? One method involves looking for the faint X-ray glow emitted by the WHIM million-degree gas. Telescopes like NASA Chandra and the European Space Agency's XMM Newton are tuned to pick up these whispers of high-energy light. But there's a catch: the signals are often drowned out by brighter X-ray sources, like galaxy clusters or active black holes. It's like listening for a quiet hum in a room full of shouting voices. Another approach capitalizes on the WHIM subtle fingerprints in the light of distant quasars. When quasar light passes through these hot filaments, heavy ions like oxygen-5 and neon-8 absorb specific X-ray wavelengths, leaving behind barely their absorption lines. Detecting these lines requires not just sensitivity, but also a bit of luck. The quasar's light must pass through a WHIM filament at just the right angle, and the filament must contain enough heavy elements to leave a trace. Even then, the signatures are often so weak they blur into the background, leaving scientists debating whether they've found a clue or just noise. Why does the WHIM matter so much? Because cosmological simulations consistently predict that it should hold 30 to 50% of the universe's normal matter. These models show how gravity, over billions of years, pulled baryons into a vast cosmic web, with galaxies forming at the densest nodes and the WHIM stretched along the filaments in between. If these simulations are right, the WHIM isn't just a curiosity. It's the universe's hidden backbone, a scaffolding of hot gas that's been hiding in plain sight. Yet, despite decades of searching, definitive proof of the WHIM existence remains just out of reach. Part of the challenge is its sheer diffuseness. A single filament might span tens of millions of light years but contain less than 10 atoms per cubic meter. That's 1 trillion times thinner than Earth's atmosphere. Even the brightest X-ray telescopes struggle to distinguish such faint signals from instrumental noise or foreground interference. And because the WHIM isn't uniformly distributed, mapping it requires surveying vast swaths of the sky, a painstaking process akin to assembling a million-piece puzzle with half the pieces missing. But the hunt is far from hopeless. In recent years, breakthroughs in data analysis and telescope sensitivity have brought us closer than ever. For example, a team using the Hubble Space Telescope's cosmic origin spectrograph claimed to detect oxygen ions in the WHIM by stacking observations from hundreds of quasars, amplifying the signal like turning up the volume on a distant radio station. Meanwhile, upcoming missions like ESA's Athena, set to launch in the late 2030s, promise to revolutionize the field with unprecedented X-ray vision, potentially turning the WHIM from a theoretical phantom into a charted reality. The WHIM represents one of the last great missing pieces in our cosmic inventory. Finding it wouldn't just solve the baryon mystery, it would reveal a hidden dimension of the universe's structure, showing us how ordinary matter weaves the unseen threads between galaxies. And that's a discovery worth chasing, no matter how faint the trail. Now, shifting our focus to the tools astronomers use to track down this elusive cosmic prey, let's talk about X-ray and ultraviolet telescopes. These instruments are like the high-tech magnifying glasses of the universe, designed to spot the faintest traces of the Warm-Hot Intergalactic Medium. Without them, the WHIM would remain nothing more than a theoretical ghost in the cosmic machinery. Take NASA Chandra X-ray Observatory, for example. Orbiting far above Earth's atmosphere, Chandra specializes in capturing high-energy X-rays, the kind emitted by the WHIM scorching gas. When million-degree plasma floats between galaxies, it releases a faint X-ray glow, a whisper of light that Chandra can pick up. But here's the catch: the signal is incredibly weak, often drowned out by brighter X-ray sources like galaxy clusters or feeding black holes. It's like trying to hear a faint melody in a room full of blaring speakers. To overcome this, astronomers sometimes focus on the shadows instead of the light. When X-rays from distant quasars pass through WHIM filaments, heavy ions like oxygen-7 or neon-9 absorb specific wavelengths, leaving behind tiny dips in the spectrum. These dips are the fingerprints of the WHIM, clues hidden in plain sight. Then there's the Hubble Space Telescope, armed with ultraviolet vision. While Chandra hunts for X-ray emissions, Hubble's cosmic origin spectrograph is tuned to detect UV absorption lines. Together, they form a cosmic tag team. Hubble's strength lies in its sensitivity to slightly cooler gas, bridging the gap between the WHIM and the cooler Lyman alpha clouds. By stacking observations from hundreds of quasars, astronomers can amplify these faint signals like turning up the contrast on a blurry photo. But even with these advanced tools, the hunt is far from easy. The WHIM signals are so sparse that they often blur into the background noise of the universe. Imagine trying to spot a single firefly's glow from miles away while surrounded by city lights. That's the challenge astronomers face, and because the WHIM isn't spread evenly, it clumps into filaments and voids. Finding it requires surveying vast stretches of sky, piecing together fragments of evidence like a cosmic detective. The payoff, though, could be revolutionary. If confirmed, the WHIM would rewrite our understanding of where and in what form half the universe's normal matter has been hiding. Every faint X-ray emission, every barely their absorption line, brings us closer to solving one of cosmology's greatest missing persons cases. And with next-generation telescopes on the horizon, the answers may finally be within reach. Now, let's step into the virtual universe where supercomputers act as cosmic architects, reconstructing the grand design of the missing baryons. While telescopes give us snapshots of the real cosmos, simulations allow us to test theories on an epic scale, painting a dynamic picture of how baryons weave through the fabric of space. At the heart of these simulations is the cosmic web, a vast, intricate network of filaments, nodes, and voids that stretches across the observable universe. Supercomputers like those running the Illustris or Eagle projects crunch mind-bending amounts of data to simulate how gravity, dark matter, and gas interact over billions of years. The result, a map of where baryons should be, revealing the warm-hot intergalactic medium as a ghostly lacework of ionized gas. These models show something fascinating. The missing baryons aren't just floating randomly. They're channeled into tendrils of gas stretching between galaxies like cosmic highways. Picture a spider's web glistening with dew. The threads are the WHIM, and the droplets are galaxies clinging to them. But here's the twist. While simulations predict this filamentary structure, actually detecting it is another story. The gas is so diffused that its X-ray or UV signals are often 1,000,000 times fainter than the glow of a single galaxy. One breakthrough came from the Millennium simulation, which traced the evolution of the universe from just after the Big Bang to today. It revealed that nearly half of all baryons end up in these filaments, too hot and spread out to shine like stars but dense enough to leave subtle imprints on light passing through them. Another key insight, the WHIM isn't static. Galactic winds powered by supernova and black holes pump baryons out of galaxies and into the web, while gravity funnels them toward clusters in slow-motion rivers of gas. Yet simulations aren't perfect. They rely on assumptions about feedback mechanisms, how energy from stars and black holes affects gas. And even the most advanced models struggle to replicate the delicate balance of heating and cooling in the WHIM. That's why astronomers compare simulated data with real observations, like a detective cross-referencing a suspect's alibi. When a simulation predicts a filament exactly where Chandra or Hubble spots an absorption line, it's a eureka moment, a hint that we're on the right track. The cosmic web simulations do more than just point to where baryons hide. They help us ask better questions. Could undiscovered physics explain why some filaments seem emptier than predicted? Are there colder strands of gas lurking undetected? With each iteration, as supercomputers grow more powerful and algorithms sharper, the virtual universe inches closer to reality, and the missing baryons inch closer to being found. Now, let's zoom in on the bustling metropolises of the cosmos galaxy clusters. These are the heavyweight champions of the universe, where hundreds or even thousands of galaxies are bound together by gravity, swirling in a sea of superheated gas. If the cosmic web is the invisible scaffolding of the universe, galaxy clusters are the glittering cities built upon it. And here's the catch. Even in these dense, energetic environments, the missing baryons problem persists. Galaxy clusters are packed with intracluster gas, a scorching plasma that fills the space between galaxies, reaching temperatures of tens of millions of degrees. This gas is so hot it emits X-rays, making it detectable by observatories like Chandra. When astronomers tally up the baryons in these clusters, they find something surprising. While the gas accounts for a significant chunk of normal matter, it's still not enough to close the gap in the cosmic inventory. In fact, the gas outweighs the stars in these clusters by a factor of 5 to 1, yet the total baryon count still falls short of theoretical predictions. Why is that? Part of the answer lies in the extreme conditions within clusters. The gas isn't just sitting still, it's a dynamic, turbulent soup, stirred by collisions between galaxies and outbursts from supermassive black holes. These processes can eject baryons out of the cluster entirely, flinging them into the surrounding cosmic web. Imagine a bustling marketplace where goods are constantly being traded, lost, or carried away. Some baryons escape into the vast intergalactic highways we've already explored, while others might cool and condense into new stars, but the accounting never quite adds up. Another clue comes from the way clusters evolve. Younger clusters, still in the process of forming, tend to hold onto more of their baryons. Over time, as they grow and merge, feedback mechanisms like the energy blasted out by supernova or active galactic nuclei push baryons out into the wider universe. It's a bit like a city losing population as people migrate to the suburbs. The cluster's gravity tries to pull the gas back, but some of it slips away, contributing to the missing baryon problem. Here's where things get even more intriguing. Some of the missing baryons might actually be hiding in plain sight. Recent studies suggest that a fraction could be tied up in ultra-diffuse gas clouds or even in faint, hard-to-detect dwarf galaxies orbiting the cluster's outskirts. Others might be lurking in cooler, denser filaments that haven't yet been heated to the point where they emit detectable X-rays. It's like searching for a missing puzzle piece only to realize it was camouflaged in the pattern all along. So, while galaxy clusters are baryon-rich environments, they're not the final answer to the mystery. They're a critical piece of the puzzle, showing us how gravity shapes the distribution of matter and how feedback mechanisms can redistribute it. But the hunt isn't over. Next, we'll turn our attention to a dazzling cosmic phenomenon that's become an unexpected tool in this search. Fast radio bursts, the universe's lightning-fast radio signals that might just hold the key to tracing the missing baryons. Now, let's shift our attention to one of the most enigmatic and electrifying phenomena in modern astronomy: fast radio bursts. These are the universe's blink and you'll miss it radio signals, fleeting bursts of energy that last just milliseconds but pack the power of hundreds of millions of suns. At first glance, they might seem unrelated to the missing baryon problem, but here's the twist. These cosmic flashes are turning out to be some of the most promising tools we have for tracking down the universe's lost matter. So, how does a brief burst of radio waves help us find something as elusive as the warm-hot intergalactic medium? The answer lies in a property called dispersion. When a fast radio burst travels through space, it doesn't move through a perfect vacuum. It passes through electrons scattered along the way, in galaxies, galaxy clusters, and especially in the diffuse WHIM. These electrons slow down the radio waves slightly, with higher frequencies arriving at our telescopes just a fraction of a second before the lower ones. The degree of this delay, known as the dispersion measure, tells us how many electrons the signal encountered on its journey. Think of it like a cosmic version of a toll booth. Every electron the radio waves pass through adds a tiny toll to their travel time. By measuring the total toll, the dispersion, we can estimate how much material the burst traveled through. And since baryonic matter, even in the WHIM, contains electrons, this gives us a way to weigh the invisible stuff between galaxies. It's as if the universe handed us a flashlight that only illuminates the very thing we're trying to find. The real breakthrough came when astronomers realized that fast radio bursts from distant galaxies could serve as backlights shining through the cosmic web. By analyzing their dispersion measures, researchers can map the distribution of electrons, and by extension, baryons along the line of sight. some of the most exciting studies have used FRBs to detect the WHIM faint filamentary structures, revealing baryons in regions too diffuse to show up in X-ray or ultraviolet surveys. But like any tool, FRBs come with challenges. First, they're incredibly rare and unpredictable. Catching one requires telescopes to be pointed at the right place at the right time. Second, disentangling the dispersion caused by the WHIM from other sources like the interstellar medium of the host galaxy or our own Milky Way is a complex puzzle. Yet, with new observatories like the Canadian Hydrogen Intensity Mapping Experiment and the upcoming Square Kilometre Array, we're poised to detect thousands more FRBs, turning them into a statistical powerhouse for baryon hunting. What makes this approach so revolutionary is its simplicity. Unlike X-rays or UV light, which rely on the WHIM being hot enough to emit detectable signals, FRBs don't care about temperature. They can probe the cooler, denser pockets of the cosmic web that other methods miss. It's like switching from a metal detector to a ground-penetrating radar. Suddenly, we're seeing layers of the universe that were previously invisible. The implications are staggering. If fast radio bursts live up to their promise, they could finally close the gap in the cosmic baryon budget, confirming that the missing matter has been hiding in the WHIM all along. But the story doesn't end here. Up next, we'll explore another clever trick astronomers use to spot these elusive baryons: quasar absorption lines, the cosmic fingerprints left on light traveling across the universe. Now, let's turn to another cosmic detective tool: quasars, the brightest beacons in the universe. These distant, ultra-luminous objects, powered by supermassive black holes, act like natural searchlights, illuminating the invisible structures between galaxies. When their light travels through the warm-hot intergalactic medium, it picks up subtle clues about the missing baryons, leaving behind a trail of spectral fingerprints for astronomers to decode. Here's how it works. As quasar light journeys across the cosmos, it passes through clouds of gas in the WHIM. Atoms in these clouds, like oxygen, hydrogen, and neon, absorb specific wavelengths of the quasar's light, creating tiny dips in its spectrum. These dips, called absorption lines, are like barcodes that reveal the composition, temperature, and density of the gas the light encountered. By analyzing these lines, scientists can map the distribution of baryons in the cosmic web, even in regions too faint to emit detectable X-rays or ultraviolet light. One of the most promising targets is oxygen. Unlike hydrogen, which dominates the universe but is often too cold or neutral to leave clear absorption traces in the WHIM, oxygen atoms are typically ionized, stripped of some electrons by the intense heat of the intergalactic environment. This makes them easier to spot in quasar spectra. When astronomers detect absorption lines from ionized oxygen, they're essentially seeing the cosmic scaffolding where missing baryons are likely hiding. But the challenge is immense. The WHIM gas is so diffuse that its absorption signals are incredibly weak, buried in the noise of the quasar's brilliant light. It's like trying to spot the shadow of a mosquito against the glare of a car's headlight. To overcome this, researchers stack multiple quasar spectra, combining their signals to amplify the faint whispers of the WHIM. Some studies, like those using the Hubble Space Telescope's Cosmic Origin spectrograph, have claimed detections of these elusive oxygen lines, offering tantalizing evidence for the missing baryons' whereabouts. Yet, even with these advances, gaps remain. Many absorption lines predicted by simulations haven't been observed, suggesting that either the WHIM structure is patchier than expected, or our current telescopes lack the sensitivity to catch its subtler signatures. There's also the complication of distinguishing WHIM absorption from gas closer to the quasar itself or within intervening galaxies. It's a cosmic game of hide and seek, where the hiders are masterfully camouflaged. What makes quasar absorption lines so powerful, though, is their precision. Unlike fast radio bursts, which provide a broad estimate of electron density along a line of sight, spectral lines can pinpoint the exact elements and physical conditions of the baryon-rich gas. This allows astronomers to reconstruct the WHIM 3D structure filament by filament. Future instruments like the James Webb Space Telescope and the European Space Agency's Athena mission aim to push these limits further, hunting for fainter lines and rarer elements that could finally settle the cosmic accounting debate. So, while quasars haven't yet delivered a full census of the missing baryons, they've given us something equally valuable, a roadmap. Each absorption line is a breadcrumb leading deeper into the cosmic web, hinting at where the universe's ordinary matter might be lurking. And as we'll see next, there's yet another piece to this puzzle: baryon acoustic oscillations, the ancient ripples that sculpted the large-scale structure of everything we see. Now, let's step back in time to uncover another piece of the missing baryons puzzle, one etched into the fabric of the universe itself. Billions of years ago, the cosmos was a seething soup of particles where ordinary matter and dark matter were locked in a gravitational tug-of-war. But when the universe was just a baby, only around 400,000 years old, something extraordinary happened. The first sound waves rippled through this primordial plasma, creating a cosmic fingerprint that still guides astronomers today. These are baryon acoustic oscillations, nature's own ruler for measuring the universe's structure. Picture this: in the early universe, particles of matter were packed tightly together, with photons, particles of light, pushing against them like a relentless cosmic wind. This created areas of high and low pressure, sending waves rippling outward. But when the universe cooled enough for atoms to form, a moment called recombination, those waves froze in place. The result: spherical shells of matter, each about 500 million light-years across, marking the maximum distance those ancient sound waves could travel before the universe went quiet. Fast forward to today, and these shells have stretched with the expansion of the universe, leaving a distinct pattern in how galaxies cluster across the cosmos. Here's why this matters for the missing baryons. Those frozen waves aren't just fossils, they're a direct link to where ordinary matter should be. By measuring the spacing between galaxies, scientists can use baryon acoustic oscillations as a standard ruler. If galaxies are consistently separated by that 500 million light-year scale, it's a telltale sign that baryons, once part of those primordial waves, are distributed in predictable ways. Surveys like the Sloan Digital Sky Survey have mapped millions of galaxies, confirming this pattern with stunning precision. But here's the catch: the galaxies we see only account for a fraction of the baryons. The rest must be hiding in the spaces between them, likely in the same warm-hot intergalactic medium we've been hunting. Baryon acoustic oscillations don't just tell us where to look, they also reveal how the universe has expanded over time. By comparing the ruler's size at different cosmic eras, astronomers can measure dark energy's influence, the mysterious force accelerating the universe's expansion. This makes BAO a double-duty tool. It helps locate missing matter while also probing the universe's fate. Yet, even with this cosmic ruler, gaps remain. Simulations suggest baryon acoustic oscillations should leave a clearer trace in the intergalactic gas than we've observed. Some of this may boil down to the limitations of our telescopes, or perhaps the missing baryons are tucked away in regions too faint to detect. Future projects like the Dark Energy Spectroscopic Instrument aim to map tens of millions of galaxies, sharpening our BAO measurements and potentially uncovering those elusive baryon pockets. What's remarkable is how these ancient sound waves connect the dots across time and space. They tie the universe's infancy to its present-day structure, offering a roadmap to the missing matter. And as we'll see next, this isn't just about filling a cosmic ledger. It's about understanding the very framework of reality. The hunt for baryons isn't over, but with tools like BAO, we're closer than ever to solving one of astronomy's greatest mysteries. But now, let's untangle a cosmic mix-up that even seasoned space enthusiasts sometimes stumble over: the difference between dark matter and missing baryons. It's easy to lump them together as stuff we can't see, but they play entirely different roles in the universe's story. start with dark matter. This mysterious substance makes up roughly 25% of the cosmos, yet it refuses to interact with light or ordinary matter in any way we've detected. It doesn't emit, absorb, or reflect photons, which is why even our most powerful telescopes draw a blank. We only know it's there because of its gravitational grip. It bends light around galaxies and keeps stars from flying apart like a spinning merry-go-round with no one holding on. Crucially, dark matter isn't made of baryons. It's something else entirely, possibly exotic particles like WHIM or actions, remnants from the universe's earliest moments. Now contrast that with missing baryons. These are the protons, neutrons, and electrons, ordinary matter, that we know must exist but can't account for. Remember, baryons built everything we see, planets, stars, even the coffee in your cup. The problem: when astronomers tally up all the visible baryons in stars and galaxies, they only find about half of what the Big Bang's leftover light, the cosmic microwave background, says should be there. Unlike dark matter, missing baryons do interact with light. They're just fiendishly hard to spot because they're spread so thin, like a handful of glitter tossed into a swimming pool. Here's where confusion creeps in. Some think dark matter is the missing baryons, but that's like mistaking the scaffolding of a building for the bricks inside. Dark matter's gravity sculpts the universe's large-scale structure, while baryons are the raw material that fills those structures. Others assume the missing baryons are hiding as dark matter, but that's impossible. Dark matter's behavior doesn't match anything made of protons or neutrons. The real answer: those lost baryons are likely floating in the warm-hot intergalactic medium, the WHIM, too diffused to glow but just dense enough to trace with clever techniques like quasars, absorption lines, or fast radio bursts. Why does this distinction matter? Because solving the missing baryon puzzle won't explain dark matter, and vice versa. Each is a separate chapter in the universe's biography. Finding the baryons would complete our map of ordinary matter, while deciphering dark matter could rewrite the laws of physics. Both quests are vital, but they're not the same. So next time you hear about the universe's invisible stuff, remember, dark matter is the silent architect shaping the cosmos from the shadows, while missing baryons are the misplaced inventory of everything tangible. One's a ghost we're still learning to measure, the other's a whisper we're learning to hear. And as we'll soon see, cracking these mysteries requires tools as diverse as the enigmas themselves. Now, let's tackle the very real roadblocks standing between us and the answer to this cosmic hide-and-seek game. Finding the missing baryons isn't just about knowing where to look, it's about overcoming the formidable challenges that make them nearly invisible to our current tools. First, consider the sheer diffuseness of the warm-hot intergalactic medium. Picture trying to spot a single light bulb in a foggy city thousands of miles wide. The WHIM density is so low, about 1 atom per cubic meter, or 1,000,000 times thinner than the best vacuum we can create in labs, that its signal drowns in cosmic noise. Unlike stars or galaxies, which blaze with concentrated light, the WHIM faint glow gets lost against the backdrop of the universe. Even when we detect it, the signal is often so weak that distinguishing it from instrument errors or other cosmic phenomena becomes a nightmare. Then there's the limitation of our telescopes. Most observatories are designed to capture bright, high-energy sources like stars or black holes, not the whisper-thin signatures of the WHIM. X-ray telescopes, for instance, struggle because the WHIM emissions are often right at the edge of their sensitivity. It's like trying to hear a pin drop in a thunderstorm. Our tools just aren't fine-tuned enough to pick up such subtle cues without drowning in interference. Even the Hubble Space Telescope, a workhorse of modern astronomy, can't see the WHIM directly. Instead, we rely on indirect methods like catching the shadowy fingerprints it leaves on light from distant quasars, a painstaking and often ambiguous process. This brings us to the third hurdle, the need for multi-wavelength teamwork. The WHIM doesn't just emit X-rays, it also absorbs ultraviolet light and subtly bends radio waves. No single telescope can capture all these signatures alone. It's like solving a jigsaw puzzle where each piece is held by a different collaborator across the globe. Coordinating observations across X-ray, UV, and radio telescopes, each with limited time and competing scientific priorities, adds layers of logistical complexity. And even when we succeed, stitching together these disparate data sets requires sophisticated models, which themselves can introduce uncertainties. But perhaps the most frustrating challenge is time. The universe isn't in a hurry to reveal its secrets. Some WHIM filaments are so vast and sparse that light takes billions of years to traverse them, and our snapshots capture only fleeting moments in their existence. Without long-term, sustained observations, something budget cycles and telescope allocation committees rarely support, we're left with incomplete puzzles where critical pieces might be missing forever. Yet, despite these obstacles, astronomers aren't giving up. Every technical hurdle is a clue in itself, pushing us to innovate. Upcoming missions, like the European Space Agency's Athena X-ray Observatory, promise 10 times the sensitivity of current tools, while radio arrays like the Square Kilometre Array could map the WHIM electron haze like never before. The chase is far from over, it's just getting smarter, and as we'll see next, the breakthroughs on the horizon might finally bring this cosmic treasure hunt to a close. Now, imagine a new era of cosmic exploration where our tools are no longer the limiting factor. The next generation of telescopes and missions is on the horizon, each designed to peel back the layers of the universe's greatest mysteries, including the elusive missing baryons. These aren't just incremental upgrades, they're revolutionary leaps that could finally tip the scales in our favor. Leading the charge is the European Space Agency's Athena, set to launch in the late 2030s. This X-ray observatory isn't just another telescope, it's a game changer. With a sensitivity 10 times greater than current instruments, Athena will scan the skies for the faintest whispers of the warm-hot intergalactic medium. Picture it like upgrading from a pair of binoculars to a high-powered microscope, capable of spotting the delicate X-ray glow of million-degree gas filaments that have eluded us for decades. Athena's wide-field imaging will map vast swaths of the cosmic web, turning what was once noise into a clear signal. But Athena won't be working alone. NASA Lynx X-ray Observatory, still in the conceptual phase, promises even sharper vision. Lynx aims to combine unparalleled resolution with deep field surveys, allowing astronomers to study the WHIM in unprecedented detail. Think of it as putting on glasses that not only correct your vision, but let you see colors you never knew existed. Lynx could reveal how baryons move between galaxies and the intergalactic medium, solving pieces of the puzzle we didn't even know were missing. Then there's the Square Kilometre Array, or SKA, a groundbreaking radio telescope network spanning 2 continents. While X-ray telescopes like Athena and Lynx hunt for hot gas, SKA will trace the WHIM electron haze by analyzing fast radio bursts, cosmic flashes that act like backlights, illuminating the invisible matter in their path. SKA's sheer scale, thousands of antennas working in unison, will provide a 3D map of the cosmic web structure, filling in gaps that other telescopes can't reach. It's like using sonar to map the ocean floor, but for the universe. What makes these missions so exciting isn't just their individual capabilities, but how they'll work together. Athena's X-ray data, combined with SKA's radio observations and Lynx's high-resolution snapshots, will create a multi-wavelength portrait of the missing baryons. This collaborative approach is key because the WHIM doesn't reveal itself in just one type of light. It's a master of disguise, hiding in plain sight across the electromagnetic spectrum. And let's not forget the role of data. These telescopes will generate staggering amounts of information, requiring artificial intelligence and machine learning to sift through the noise. Algorithms will scan for patterns, flagging subtle signals that human eyes might miss. It's a marriage of cutting-edge hardware and software, where each breakthrough in computing power brings us closer to solving the mystery. The road ahead is long. These missions won't launch overnight, but the payoff could redefine our understanding of the universe. For the first time, we're not just hoping to find the missing baryons, we're building the tools to ensure they can't stay hidden much longer. And as we'll see next, the scientific community is already buzzing with theories about what these discoveries might reveal. While these future telescopes promise to revolutionize our search, scientists haven't been sitting idle. Groundbreaking studies are already pushing the boundaries of what we know about the missing baryons. One of the most talked about discoveries comes from a team led by astronomer Fabrizio Nicastro. Using data from the Chandra X-ray Observatory and the European Space Agency's Newton, Nicastro and his colleagues claim to have detected the Warm-Hot Intergalactic Medium in action. Their study focused on the light from a distant quasar which acted like a cosmic flashlight. As this light traveled through space, it passed through filaments of the WHIM, leaving faint absorption lines in the X-ray spectrum like fingerprints of the missing baryons. Nicastro's findings, published in the journal Nature, suggested they'd found a significant reservoir of ionized oxygen gas, a key tracer of the WHIM. The implications were huge. If confirmed, this would mean we'd finally pinpointed one of the hiding spots for the universe's lost matter. But as with any major claim in science, skepticism followed. Other researchers questioned whether the detected signal was strong enough to rule out alternative explanations. Could it have been noise in the data or contamination from other sources? The debate highlighted just how tricky it is to study something as faint and diffuse as the WHIM, even with our best instruments. Another team, led by astronomer Juna Kollmeier, took a different approach. Instead of hunting for the WHIM directly, they used supercomputer simulations to predict where baryons should be, then compared those predictions with real observations. Their results, published in the Astrophysical Journal, suggested that the missing baryons aren't missing at all, they're just hiding in plain sight, spread so thinly across the cosmic web that our current tools struggle to see them. Kollmeier's work added fuel to the debate, showing that the WHIM elusive nature might simply be a matter of sensitivity. If we could build telescopes powerful enough, the missing baryons might turn out to be exactly where models say they should be. Then there's the work of astronomers like Jessica Work, who studies how galaxies lose baryons over time. Her research suggests that supernova explosions and active galactic nuclei, the violent cores of distant galaxies, could be ejecting baryons into intergalactic space at incredible speeds. These galactic winds might explain why some baryons seem to vanish from galaxies, only to reappear as part of the WHIM. Work's findings, combined with simulations, paint a picture of a dynamic universe where baryons are constantly on the move, cycling between galaxies and the vast cosmic web. Despite these advances, the field remains divided. Some researchers argue that the WHIM alone can't account for all the missing baryons, pointing to gaps in our understanding of how matter behaves in extreme environments. Others believe the solution lies in refining our models, accounting for overlooked processes like turbulence or magnetic fields in the intergalactic medium. What's clear is that each new study brings us closer to an answer, but also raises new questions. As we'll see next, these controversies aren't just academic. They're driving the next wave of missions designed to settle the debate once and for all. Now, let's untangle the heated debates swirling around these discoveries. Not everyone is convinced the Warm-Hot Intergalactic Medium tells the whole story of the missing baryons. While many researchers see the WHIM as the prime suspect, others argue the evidence isn't yet strong enough to close the case. Some scientists, like theoretical cosmologist Joseph Silk, have proposed more exotic explanations like primordial black holes. These ancient hypothetical objects formed in the chaos of the early universe could theoretically lock away baryons in their immense gravitational grip. If they exist, they'd be nearly invisible to our telescopes, making them perfect hiding places for missing matter. But here's the catch. No one has definitively detected a primordial black hole, leaving this idea in the realm of fascinating speculation. Then there's the camp led by astronomers like Maxim Markovich, who question whether the WHIM estimated mass adds up. Even if we account for all the ionized gas filaments we've spotted, the numbers might still fall short of the full baryon budget. Markovich's work with galaxy clusters suggests some baryons could be lurking in even hotter, more diffuse regions of the intergalactic medium, places so energetic that current X-ray telescopes can't pick up their faint signals. Others, like astrophysicist Romain Tessier, argue that supercomputer simulations might be underestimating how much baryons clump together on small scales. If true, pockets of dense, cool gas could be hiding in the cosmic web, camouflaged against the background. But perhaps the most provocative challenge comes from those who think we're missing something fundamental about physics itself. Could there be unknown particles or forces subtly altering how baryons behave? Some theories suggest certain dark matter interactions might disguise ordinary matter in ways we don't yet understand. It's a radical idea, but as physicist Chandra Weinstein points out, radical gaps in our knowledge sometimes require radical solutions. Amidst this clash of ideas, one thing is certain: the controversy is pushing science forward. Every challenge to the WHIM hypothesis forces researchers to sharpen their models, design better experiments, and dig deeper into the data. And as we'll soon see, the next generation of telescopes aims to settle these debates by bringing the hidden universe into focus like never before. As we peel back the layers of cosmic mystery, some scientists dare to venture beyond the edges of conventional theories, asking whether the universe's missing baryons could be hiding in plain sight, just not in ways we've thought to look. One compelling but controversial idea suggests that baryons might be tucked away inside compact cosmic objects, like rogue planets or failed stars known as brown dwarfs. These dim, cold objects drift between galaxies, nearly invisible to our telescopes. If enough of them exist, they could collectively account for a significant chunk of the missing matter. But here's the problem. Surveys scanning the skies for such objects haven't found them in the numbers needed to solve the puzzle. Then there's the wild card of alternate physics theories that tweak the fundamental rules we thought were set in stone. For instance, some researchers propose that baryons might decay into exotic particles over cosmic timescales, slowly vanishing from the observable universe. While particle physics experiments have found no evidence for this, the idea lingers because it hints at gaps in our understanding of matter's stability. Another fringe concept involves mirror matter, a shadowy parallel form of baryons that interacts only weakly with the familiar universe. If real, these mirror particles could be weaving through space undetected, masquerading as missing mass. But how credible are these alternatives compared to mainstream models like the Warm-Hot Intergalactic Medium? Most astronomers argue that exotic theories, while tantalizing, lack the direct evidence that the WHIM has begun to accumulate. For example, while primordial black holes or mirror matter make for gripping headlines, they often require introducing new, unproven physics. In contrast, the WHIM fits within our current understanding of the universe. It's just fiendishly hard to observe. That said, history has shown that some of science's greatest leaps began as fringe ideas. The key is balancing open-mindedness with rigorous skepticism, testing each hypothesis against the growing mountain of data. What's fascinating is how these debates reveal the creative tension driving cosmology forward. Whether the answer lies in hidden cosmic structures or revolutionary physics, the hunt for the missing baryons is far from over. And as we'll see next, the tools to crack this case might already be on the horizon, waiting to reveal what's been hiding in the universe's darkest corners. Now, let's shift our gaze to the engines of cosmic redistribution supernova and active galactic nuclei. These titanic forces don't just sculpt galaxies, they might also be the key players in flinging baryons into the vast intergalactic wilderness. Picture a supernova, the explosive death of a massive star. In its final moments, it doesn't just fade quietly, it blasts out shockwaves powerful enough to hurl surrounding gas packed with baryons clear out of its host galaxy. This isn't a gentle nudge, it's a cosmic catapult sending matter flying at speeds that defy gravity's grip. Over billions of years, countless supernovae could have collectively ejected enough material to account for a significant fraction of the missing baryons, scattering them into the thin, hard-to-detect reaches of the intergalactic medium. But supernovae aren't the only culprits. Enter active galactic nuclei, the monstrous hearts of galaxies where supermassive black holes feast on surrounding matter. As these black holes devour gas and stars, they don't just swallow everything. Some of the material gets funneled into jets and winds that erupt outward at nearly the speed of light. These jets act like cosmic fire hoses, spraying baryons far beyond their home galaxies. Imagine a garden hose turned up to interstellar pressures. The sheer force can push gas clear out into the space between galaxies, where it joins the diffuse reservoir of the warm-hot intergalactic medium. What's fascinating is how these processes aren't just chaotic, they're part of a delicate feedback loop. When too many baryons get ejected, star formation in the galaxy slows down like a factory running out of raw materials. This self-regulating mechanism ensures galaxies don't grow unchecked, but it also means baryons are constantly being recycled between galaxies and the intergalactic medium. It's a cosmic game of catch and release, with supernova and active galactic nuclei as the players tossing baryons back and forth. Yet, proving this happens on the scale needed to explain the missing baryons is tricky. Simulations show these feedback mechanisms can eject plenty of material, but observations struggle to catch them in the act. Detecting baryons mid-flight, especially in the faint outskirts of galaxies, requires telescopes with unprecedented sensitivity. That's where upcoming missions like the European Space Agency's Athena and NASA links come in. They're designed to spot these faint whispers of ejected gas, turning theoretical predictions into observable reality. So, while supernova and active galactic nuclei might not single-handedly solve the missing baryon puzzle, they're crucial pieces of the story. They remind us that the universe isn't static, it's a dynamic, ever-changing arena where matter is constantly on the move. And as we'll see next, even the earliest epochs of cosmic history might hold clues to where these wandering baryons have gone. To understand how the missing baryons might have been scattered across the cosmos, we need to rewind the clock to one of the universe's most transformative eras, the epoch of reionization. Picture this: roughly 400 million years after the Big Bang, the cosmos was a dark, murky place filled with neutral hydrogen gas. Then, something extraordinary happened. The first stars and quasars flickered to life, flooding the universe with ultraviolet light so intense it ripped electrons from atoms, turning neutral gas into a sea of ionized plasma. This was reionization, a cosmic dawn that didn't just illuminate the universe, it fundamentally reshaped where baryons could hide. These early stars weren't like the ones we see today. They were behemoths, hundreds of times more massive than our Sun, burning fiercely and dying young in colossal supernovae. Their ultraviolet radiation acted like a cosmic blowtorch, ionizing vast bubbles of gas around them. Over time, these bubbles overlapped, creating a web of ionized regions that eventually filled the entire universe. Quasars, the luminous cores of young galaxies powered by voracious black holes, amplified this process. Their jets and radiation reached even farther, punching through the remaining pockets of neutral gas and ensuring reionization was complete by around 1 billion years after the Big Bang. But here's the critical link to the missing baryons. This ionization didn't just light up the universe, it redistributed its matter. The energy from reionization heated the gas, making it expand and become more diffuse. Think of it like turning a block of ice into steam. The molecules are the same, but they're now spread far apart and harder to track. This heated, ionized gas likely became part of the warm-hot intergalactic medium, that elusive reservoir where many missing baryons might reside. The process didn't just scatter baryons, it also made them harder to detect, as ionized gas doesn't absorb light the way neutral gas does. What's more, reionization wasn't a gentle process. The violent feedback from early stars and quasars could have ejected baryons from galaxies entirely, similar to how supernova and active galactic nuclei do today. Simulations suggest that the combined radiation and shock waves from these ancient powerhouses might have pushed gas into the intergalactic void, where it remains faint and overlooked. This means the seeds of the missing baryon problem could have been planted over 13 billion years ago during this turbulent period, yet piecing together this story isn't easy. The light from the epoch of reionization is incredibly faint, stretched into infrared wavelengths by the expansion of the universe. Telescopes like the James Webb Space Telescope are now peering into this era, hunting for clues about how reionization unfolded and how it shaped the baryon distribution we're trying to measure today. By studying the ancient galaxies and quasars that drove this process, we might finally trace the path of those missing baryons, from their fiery origins to their current hiding places in the cosmic web. So, while reionization might seem like a distant chapter in cosmic history, its echoes are everywhere. The universe's struggle to balance matter and energy, to build galaxies and scatter their raw materials, began in this epoch. And as we'll see next, this cycle of cosmic recycling where baryons are lost and found is still unfolding in ways we're just beginning to understand. Now, let's zoom out and see the bigger picture, because the story of missing baryons isn't just about where they've gone, but how they move. Imagine the universe as a giant recycling plant where matter isn't lost, just endlessly repurposed. This is baryon cycling, a cosmic dance where gas is pulled into galaxies, pushed out by violent events, and scattered across the vast intergalactic voids, only to be drawn back in again over billions of years. Take a typical galaxy like our Milky Way. Right now, it's sipping on gas from its surroundings, a delicate inflow of pristine hydrogen, the fuel for future stars. But it's also spewing out material. Supernova, the explosions of massive stars, act like cosmic pressure washers, blasting gas out into the surrounding medium. Meanwhile, supermassive black holes at galactic centers unleash even more energy. When these black holes feed, they power jets and winds that can fling baryons clear out of their host galaxies. This isn't destruction, it's redistribution. The gas doesn't vanish, it joins the intergalactic medium, or WHIM, where it mingles with other exiled baryons. Here's where it gets fascinating. That ejected gas doesn't stay lost forever. Gravity, the universe's great recycler, slowly pulls these baryons back. Over time, they cool and condense, flowing along filaments of the cosmic web, the same structures that feed galaxy clusters. Some of this gas might even end up in the warm-hot intergalactic medium, or WHIM, that elusive fog of ionized particles we've been hunting. It's a slow process, taking billions of years, but it means today's missing baryons could be tomorrow's starlight. But the cycle isn't perfect. Some gas gets heated so violently it escapes the gravitational pull of galaxies entirely, joining the truly diffuse outskirts of the cosmic web. Other baryons might be trapped in low-density regions, too spread out to detect easily. And let's not forget the role of cosmic weather turbulence, magnetic fields, and collisions between galaxy clusters all stir the pot, making baryon tracking even trickier. What's wild is that we're seeing this cycle in action right now. Instruments like the Hubble Space Telescope have spotted galactic fountains, gas ejected by star formation that later rains back down. Simulations show giant gas clouds around galaxies, the remnants of past outflows waiting to be reclaimed. Even our own Milky Way has a halo of hot gas, evidence of this endless give and take. So when we talk about missing baryons, we're really talking about a universe that's thrifty with its matter. Nothing is wasted, it's just constantly on the move, hidden in plain sight. The challenge isn't just finding these baryons, but untangling the intricate paths they've taken over cosmic time. And as we'll see next, cutting-edge tools are finally giving us the keys to trace this grand recycling system in detail. But here's the catch: simulating this cosmic recycling isn't as straightforward as it sounds. Picture trying to map every raindrop in a hurricane while only seeing the storm from space. That's the challenge astrophysicists face when modeling baryon cycling. Even with today's supercomputers, simulations hit hard limits. For starters, there's the issue of resolution. The universe is vast, and tracking every atom is impossible. So, scientists use shortcuts, simulating large volumes of space but treating gas as smooth fluid rather than individual particles. This works for big-picture trends, but it misses fine details like tiny gas clouds or turbulent eddies that could hide baryons. Then there's the physics itself. We don't fully understand all the forces at play. Take feedback mechanisms, those explosive events like supernova and black hole jets that shove baryons around. Models approximate their effects, but approximations aren't perfect. A supernova's energy might be spread evenly in a simulation, while in reality, it's chaotic, blowing bubbles in some areas and leaving others untouched. These inaccuracies add up, skewing where baryons appear in virtual universes versus the real one. Even the cosmic web structure poses problems. Filaments of the WHIM are wispy, spanning millions of light years, but with densities barely above a vacuum. Simulating such faint, sprawling networks demands absurd computational power. To save time, researchers often focus on small patches, but that risks missing large-scale flows that ferry baryons between galaxies. It's like trying to predict global weather by only studying a single city. And let's not forget the unknowns: magnetic fields, cosmic rays, and even exotic physics like quantum turbulence could influence baryon movement, factors rarely included in models because their effects are poorly measured. Without these pieces, simulations are like recipes missing key ingredients. They might produce something resembling the universe, but the finer flavors, like the exact distribution of missing baryons, get lost. Yet progress is happening. Cutting-edge projects like Illustritingy and Eagle are weaving more physics into their codes, from refined feedback recipes to better gas chemistry. Each iteration brings virtual universes closer to reality, narrowing the gap between predicted and observed baryons. But until we can simulate the cosmos at full fidelity, the hunt for missing matter will remain part science, part art. Now, let's step back and see how this cosmic puzzle connects to other big questions in science. The hunt for missing baryons isn't just about filling a gap in our cosmic inventory. It ripples across disciplines, from the tiny world of particle physics to the grand fate of the universe itself. Take neutrinos, for example. These ghostly particles barely interact with matter, yet they could hold clues about baryons. Some theories suggest neutrino mass might influence how baryons move through the cosmic web. If neutrinos are heavier than we think, their gravity could subtly tug baryons into hard-to-detect regions. It's like tracing invisible ink by watching how it bends the paper underneath. Particle colliders, like the Large Hadron Collider, are probing neutrino properties, and their findings might indirectly shine a light on where baryons are hiding. Then there's cosmology, the universe's ultimate destiny. Whether it keeps expanding, collapses, or tears apart depends on its total matter content. Missing baryons play a role here. If they're lurking in the WHIM, their gravitational pull could slightly slow cosmic expansion. But if they're somehow lost beyond detection, our models of the universe's fate might need tweaking. It's like trying to predict a marathon runner's finish time without knowing if they've got a water bottle weighing them down. Even quantum mechanics gets a seat at the table. Some fringe theories propose that baryons might briefly phase shift into exotic quantum states, making them invisible to our telescopes. While this sounds like science fiction, it's a reminder that the rules governing the very small could rewrite the story of the very large. And don't forget astrophysical chemistry. The WHIM ionized gas is a soup of elements forged in stars. Tracking missing baryons could reveal how metals like oxygen and iron spread across the cosmos, enriching future generations of stars and planets. It's a cosmic recycling program we're only beginning to understand. What's fascinating is how these threads weave together. A particle physicist studying neutrinos or a cosmologist modeling the universe's end might seem worlds apart, but both are chasing pieces of the same puzzle. Every discovery about baryons sends shockwaves through science, proving that in the universe everything is connected. The next big breakthrough might not come from a telescope, but from a lab, a supercomputer, or even a theory we haven't dreamed up yet. Now let's untangle a common misconception that often clouds this cosmic mystery. Headlines love to scream things like, "Scientists can't find half the universe." But that's a dramatic oversimplification. The truth is far more nuanced and, frankly, more fascinating. The missing baryon problem isn't about ignorance, it's about precision. Scientists aren't staring at the cosmos, baffled. They've narrowed down the possibilities to a few likely hiding spots, like the Warm-Hot Intergalactic Medium. The challenge, detecting something so diffuse, is like trying to spot a single lit match in a foggy stadium. It's not that we don't know where to look, it's that our tools haven't quite caught up to the task. Media often paints this as a failure, but it's actually a testament to how far we've come. A century ago, we didn't even know other galaxies existed. Now we're debating the temperature of gas filaments billions of light years away. The gap between theory and observation isn't a flaw, it's the frontier where discovery happens. Another oversimplification, the idea that baryons are missing like lost keys. In reality, they're probably just camouflaged. Imagine painting a white thread white and laying it on a white tablecloth. You know it's there, but your eyes can't pick it out. Similarly, the WHIM faint X-ray emissions blend into the cosmic background. New telescopes, like the upcoming Athena mission, are essentially crafting better cameras to capture this elusive thread. Then there's the false equivalence with dark matter. Dark matter is truly mysterious, an entirely unknown substance. Missing baryons, though, they're ordinary matter playing hard to get. This distinction matters because it shapes how we search. For baryons, we refine detection methods. For dark matter, we're still guessing at the rules. The media also skips over the collaborative detective work involved. Astronomers, particle physicists, and simulators team up, cross-checking data from quasars, galaxy clusters, and supercomputers. It's less like a single detective missing a clue and more like a global team piecing together a billion-piece puzzle where half the pieces are transparent. So next time you hear half the universe is missing, remember, science isn't about easy answers, it's about asking better questions. And every time we sharpen those questions, like refining how we weigh the cosmos or model gas filaments, we're not admitting defeat. We're inching closer to the light. Here's the next section of the script, seamlessly continuing from the previous segment while introducing new insights in an engaging, accessible way. Now, here's the exciting part. You don't need a PhD or $1 billion telescope to join this cosmic treasure hunt. The search for missing baryons isn't just for professional astronomers. Thanks to citizen science projects, anyone with curiosity and an internet connection can help peel back the layers of this mystery. Take Galaxy Zoo, for example. This groundbreaking initiative invites volunteers to classify galaxies imaged by telescopes like Hubble. By sifting through millions of galaxy-shaped spirals, ellipticals, mergers, amateurs have uncovered rare structures that even algorithms missed. These classifications aren't just busy work, they feed directly into research mapping the cosmic web. helping scientists trace where baryons might be hiding in galaxy clusters or their outskirts. It's like crowdsourcing the world's most detailed celestial map, one click at a time. Then there's the hunt for fast radio bursts, or FRB. These fleeting cosmic signals are gold mines for probing the Warm-Hot Intergalactic Medium. Projects like SETI at home or the Australian-led Einstein at home let users donate idle computer power to analyze radio telescope data. Your laptop could help spot an FRB's telltale dispersion, a clue to how many electrons and thus baryons it passed through on its way to Earth. It's detective work on a galactic scale, and every participant gets a front row seat. But the opportunities don't stop there. Platforms like Zooniverse host projects where volunteers tag gas filaments in X-ray images or flag unusual quasar spectra, tasks that train AI to better recognize faint WHIM signatures. Even stargazers with backyard telescopes can contribute by monitoring variable stars, whose light might subtly reveal intervening baryon-rich gas. What makes these projects revolutionary isn't just the data they gather. It's the democratization of discovery. When a retired teacher in Portugal or a high schooler in Kenya spots something unexpected, it reminds us that science isn't an ivory tower. It's a collective human effort fueled by shared wonder, and in a puzzle as vast as the missing baryons, every pair of eyes or lines of code counts. So, while billion-dollar telescopes like Athena or the Square-Kilometre Array will undoubtedly revolutionize the search, never underestimate the power of a curious mind with a Wi-Fi connection. The next clue to the universe's biggest hide-and-seek game could come from someone just like you. And speaking of revolutionary tools, let's turn our attention to the cutting-edge missions poised to transform this field, because the future of baryon hunting is brighter than ever. Now, let's tackle a question that often sparks heated discussions in the world of astrophysics. Where should we direct our limited resources in the quest to understand the universe? The hunt for missing baryons sits at a fascinating crossroads, competing for funding and attention with other big-ticket items like dark matter research and the search for habitable exoplanets. It's not just a scientific debate, it's a reflection of what we, as a society, value most in our exploration of the cosmos. Take dark matter, for example. It dominates headlines and research budgets because it makes up roughly 85% of the universe's matter. Solving its mystery could rewrite physics as we know it. But here's the catch: ignoring the missing baryon problem means leaving half of the universe's normal matter unaccounted for. Without knowing where these baryons are, our models of galaxy formation, cosmic evolution, and even the fate of the universe remain incomplete. It's like trying to solve a jigsaw puzzle when half the pieces are scattered under the table. Then there's exoplanet research, which captures public imagination like few other fields. Discovering another Earth or signs of alien life is undeniably thrilling. But consider this: understanding baryons helps us grasp the very building blocks that make planets, stars, and even potential life possible. If we don't know how matter is distributed and recycled across the cosmos, how can we truly understand the conditions that give rise to habitable worlds? Funding isn't infinite, and tough choices have to be made. Some argue that baryon research is niche compared to the transformative potential of dark matter breakthroughs or the cultural impact of exoplanet discoveries. Others counter that neglecting baryons leaves a glaring hole in our cosmic ledger, one that affects everything from galaxy simulations to the accuracy of future telescopes. There's also the ethical dimension. Should taxpayer money fund what might seem like abstract detective work, or should it prioritize research with more immediate, tangible benefits? The answer isn't simple. While finding missing baryons won't cure diseases or solve energy crises, it sharpens our tools for probing the universe, tools that often spin off into unexpected technological advancements. X-ray astronomy, for instance, has roots in military and medical imaging. What's clear is this: each field informs the others. Dark matter maps influence where we look for baryons. Exoplanet atmospheres reveal how matter behaves under extreme conditions, and baryon studies refine our understanding of cosmic chemistry. Instead of pitting them against each other, perhaps the real challenge is designing missions and telescopes that can tackle multiple mysteries at once. With that in mind, let's shift our gaze to the philosophical side of this puzzle, because sometimes the biggest questions aren't just about what we find, but why we search in the first place. But stepping back from the telescopes and data charts for a moment, let's consider something deeper. What does the hunt for missing baryons tell us about our place in the universe? This isn't just a scientific puzzle, it's a humbling reminder of how much we still don't know. Think about it. Here we are, a species that's mapped every corner of our planet, sent probes beyond our solar system, and peered back to the dawn of time itself. Yet half of the universe's normal matter, the very stuff we're made of, has slipped through our fingers. It's a cosmic irony that echoes some of history's greatest scientific mysteries. Take dark energy, for example. A century ago, we thought the universe was static. Then we discovered it's not just expanding but accelerating, driven by some invisible force we still can't explain. Dark energy shattered our assumptions just as the missing baryon problem does today. Both reveal how our confidence often outpaces our understanding. We build grand theories only for the cosmos to whisper back, "Not so fast." And that's the beauty of it. Science isn't about having all the answers. It's about asking better questions. Every time we think we've got the universe figured out, like when Newton's laws seemed absolute, or when we assumed the Milky Way was the entire cosmos, reality nudges us toward a bigger picture. The missing baryons are that nudge right now. They force us to question whether our tools are sharp enough, our models precise enough, or if we're even looking in the right places. But here's the thing, this isn't cause for frustration, it's inspiration. Consider how past mysteries have reshaped our worldview. The discovery of cosmic microwave background radiation turned the Big Bang from speculation into fact. The realization that galaxies rotate faster than they should revealed dark matter's grip on the cosmos. Each gap in our knowledge has been a stepping stone, not a stop sign. The baryon problem is no different. It's a call to innovate, to build better detectors, refine our simulations, and maybe even rethink some fundamentals. And let's not forget the cultural ripple effects. Struggling with these questions reminds us that science isn't a solo endeavor. It's a collective journey, one that spans generations. The astronomers who first noticed the missing baryon problem won't be the ones to solve it. That honor will go to their successors, just as Einstein stood on the shoulders of Newton. There's something profoundly human about that, the idea that progress isn't instant but earned, brick by brick, over lifetimes. So while we might not have the answers today, the search itself is transformative. It teaches patience, curiosity, and humility, qualities we could use more of, both in science and beyond. Because at its core, the missing baryon problem isn't just about matter. It's about what happens when we dare to admit we don't know something, and then set out to change that. Now, as we turn our attention to the cutting-edge tools that might finally crack this mystery, remember, every great discovery begins with a question we couldn't answer. And right now, the universe has given us a big one. But here's where things get exciting, because the missing baryon problem isn't just a challenge, it's a launchpad for innovation. Imagine a new generation of tools so advanced they could rewrite the rules of cosmic detective work. Let's start with quantum sensors, devices that harness the bizarre laws of the quantum world to detect the faintest whispers of matter. Picture this: while today's instruments struggle to spot the wispy tendrils of the warm-hot intergalactic medium, quantum sensors could amplify those signals, turning cosmic static into a clear radio station. By exploiting quantum entanglement, where particles remain connected across vast distances, these sensors might trace the elusive baryons hiding in the universe's emptiest voids. Then there's artificial intelligence, not just as a tool but as a partner in discovery. Current telescopes generate avalanches of data, but sifting through it is like finding needles in a galaxy-sized haystack. Enter AI-driven analysis capable of spotting patterns no human eye could catch. Imagine an algorithm trained on millions of simulated universes, learning to recognize the spectral fingerprints of missing baryons in real observations. It's not science fiction. Teams are already using machine learning to identify subtle distortions in quasar light that hint at invisible gas clouds. As AI grows smarter, it could uncover baryon-rich regions we've overlooked for decades. But why stop at Earth-bound solutions? Space-based interferometers, networks of satellites working in unison, could change the game. Picture a fleet of observatories orbiting the Sun, their combined vision sharper than any single telescope. Freed from Earth's atmospheric blur, they'd scan the cosmic web in ultraviolet and X-ray wavelengths with unprecedented clarity. Projects like the proposed Laser Interferometer Space Antenna LISA aim to detect gravitational waves, but similar tech could map baryon distribution by measuring how light bends through intergalactic plasma. The key advantage: scale. Ground telescopes are limited by geography, but space interferometers could span millions of miles, offering a panoramic view of the universe's hidden architecture. And let's not overlook the potential of neuromorphic computing, chips designed to mimic the human brain's efficiency. Traditional computers brute force calculations, but neuromorphic systems could model the cosmic web's chaotic dynamics in real time, predicting where baryons might pool. Pair that with advancements in spectroscopy, and suddenly, the warm-hot intergalactic medium isn't so invisible anymore. The beauty of these technologies is their synergy. Quantum sensors could feed data to AI, which guides space interferometers to high-probability targets, creating a closed loop of discovery. It's a reminder that solving the baryon mystery isn't about one silver bullet but a constellation of breakthroughs. And while these tools are still on the horizon, their promise is clear. They're not just closing gaps in our knowledge, they're opening doors to a universe we've only begun to imagine. As we stand on the brink of this technological revolution, one thing is certain: the missing baryons won't stay hidden forever. The next decade could redefine our cosmic senses, proving once again that the universe's greatest mysteries are invitations to innovate. Now, let's zoom out even further, because beyond the tools and the data lies a deeper question. What if the missing baryons aren't just hidden, but hint at something fundamentally new about the laws of physics themselves? Now, let's venture into the realm of the truly profound, where the missing baryons might not just be hiding, but could be rewriting the very fabric of physics. Grand Unified Theories, or JUTs for short, represent one of the most ambitious attempts to bridge the gaps in our understanding of the cosmos. These theories aim to unify the fundamental forces of nature: electromagnetism, the strong nuclear force, and the weak nuclear force under a single framework. But here's the twist: they might also hold clues to the baryon mystery. Take baryon asymmetry, for instance. Our universe is dominated by matter, with very little antimatter to be found. Yet, according to the laws of physics, the Big Bang should have created equal amounts of both. So where did all the antimatter go? Some grand unified theories propose that slight imbalances in the early universe could have favored matter over antimatter, leaving us with the baryon-rich cosmos we see today. If these theories are correct, the missing baryons might not be missing at all. They could be part of a larger cosmic imbalance we're only beginning to grasp. Then there's the tantalizing idea of hidden dimensions. String theory, a leading candidate for a grand unified theory, suggests that our universe might have more than the three spatial dimensions we experience. These extra dimensions could be curled up so tightly that they're invisible to our current instruments. But what if some of the missing baryons are leaking into these hidden realms? It's a wild thought, but not entirely implausible. If baryons interact weakly with these extra dimensions, they could exist just beyond our detection, like shadows on the wall of a higher dimensional space. But grand unified theories aren't just about abstract ideas, they have real, testable consequences. For example, many GUTs predict the existence of new particles, like magnetic monopoles or super-heavy neutrinos, which could interact with baryons in ways we haven't yet observed. Experiments at particle colliders, like the Large Hadron Collider, are actively searching for these exotic particles. Finding them wouldn't just validate grand unified theories, it could point us toward the hidden reservoirs of baryons we've been searching for. What's fascinating is how these theories connect the very large to the very small. The behavior of baryons in the vast cosmic web might be governed by physics operating at scales 1 billion times smaller than an atom. It's a reminder that the universe doesn't neatly separate its mysteries. The missing baryons could be tied to questions about the birth of the cosmos itself. As we push the boundaries of both theory and observation, one thing becomes clear. The search for the missing baryons isn't just about filling a gap in our cosmic ledger. It's about uncovering deeper truths about how the universe works, and perhaps discovering that the answers lie in places we haven't even thought to look yet. So the next time you gaze up at the night sky, remember, the stars and galaxies we see are only half the story. The rest might be written in the language of dimensions we can't yet see, or forces we've yet to name. Now, let's bring it all together. The hunt for the universe's missing baryons has taken us from the depths of galaxy clusters to the faint, glowing filaments of the warm-hot intergalactic medium. While the WHIM remains elusive, the evidence pointing to it as the primary hiding place for these baryons is compelling. Observations from X-ray and ultraviolet telescopes, combined with the dispersion measures of fast radio bursts, have painted a picture of a vast, diffuse web of ionized gas stretching between galaxies. Supercomputer simulations align with these findings, predicting that a significant portion of the universe's normal matter is woven into this cosmic tapestry, too faint and too spread out for easy detection. Yet, even as the WHIM emerges as the leading candidate, questions linger. Why haven't we detected more of it directly? Are there pockets of baryons hiding in even more unexpected places, or could our models still be missing a piece of the puzzle? Science, after all, thrives on these unanswered questions. They drive innovation, pushing us to build better telescopes, refine our simulations, and rethink our assumptions. The missing baryon problem isn't just a gap in our knowledge, it's an invitation to explore, to challenge what we think we know about the universe, and that's the beauty of astronomy. Every mystery solved often reveals new ones, each more fascinating than the last. The WHIM might hold half the universe's normal matter, but understanding it fully could unlock secrets about cosmic evolution, the nature of dark matter, and even the fundamental forces that shape reality. The journey doesn't end here. With next-generation telescopes like Athena and the square-kilometer array on the horizon, we're poised to peel back another layer of the cosmic onion. So what can you do? Stay curious, follow the discoveries as they unfold, support scientific research, and maybe even join the hunt yourself through citizen science projects. The universe is a story still being written, and each of us has a role to play in uncovering its secrets. Whether those missing baryons are hiding in the WHIM, extra dimensions, or somewhere we haven't even imagined yet, one thing's certain: the search is far from over. If you've enjoyed this deep dive into the cosmos, don't forget to like, subscribe, and hit that notification bell so you never miss an update. And let us know in the comments where you think the missing baryons are hiding. Your thoughts might just spark the next big idea. Until next time, keep looking up. The universe has plenty more surprises in store. Before we wrap up, let's take a moment to reflect on what we've uncovered together. The universe's missing baryons, those elusive building blocks of everything we see, aren't just a cosmic accounting error. They're a reminder of how much we still have to learn about the vast, intricate web of existence. From the faint glow of the warm-hot intergalactic medium to the cutting-edge tools hunting for it, this mystery connects us all to the grand story of discovery. Now here's where you come in. If this journey through the cosmos sparked your curiosity, don't let it end here. Hit that like button to let us know you enjoyed the exploration, and subscribe so you never miss out on the next deep dive into the universe's biggest puzzles. Your support helps keep the lights on for more content like this, and because science is a conversation, not a monologue, we'd love to hear your thoughts. Drop a comment below. Where do you think the missing baryons are hiding? In the shadows of galaxy clusters, tangled in the cosmic web, or somewhere even stranger? Your ideas might just inspire the next breakthrough. Finally, share this video with someone who loves a good cosmic mystery. The more people we have looking up and asking questions, the closer we get to solving the universe's secrets. Thanks for joining me on this adventure through space and time. Until next time, keep wondering, keep exploring, and remember, the universe always has another surprise up its sleeve. See you among the stars.